Hi, I'm Ozlem, and today we are going to cover the algorithm analysis module. This area of study is fascinating because it allows us to predict the performance of our algorithms, ensuring that we can develop efficient and effective solutions to computational problems. Let's dive in. So we are going to do this in four parts. 1 through 3, we are going to look at the definitions and conceptual understanding. And then in part 4, we will look at some examples. So understanding algorithms and their importance. What is an algorithm, firstly? An algorithm is a set of instructions or a procedure for solving a problem or accomplishing a task. In computer science, algorithms are the backbone of programming. Whether sorting data or searching through a database, algorithms help us to perform these tasks efficiently. So the key to this efficiency lies in understanding computational complexity, which is what we analyze in algorithm analysis. And what is computational complexity? Computational complexity helps us understand the resources required by an algorithm in terms of time and space. Time as in how long it takes to run, and space as in how much memory it uses. This is crucial because for large inputs, an efficient algorithm can mean the difference between a task finishing in milliseconds or taking centuries to complete. So here are some different growth rates and for big O analysis, functions from best to worst, constant, logarithmic, linear, log linear, polynomial, exponential, and factorial. And algorithm growth rates. One of the main objectives of algorithm analysis is to identify the common growth rates of algorithms. These rates often expressed using big O notation. It helps us compare the efficiency of algorithms as the size of the input data grows. So it is dependent on the input data. So let's go through some of the examples to clarify these concepts. Let's look at two loops, for loops with on and on squared complexities. Here's a simple loop iterating from 0 to n. This the computational complexity of this loop is on because the execution time increases with respect to n linearly. So the loop runs n times, 0 to n, and the complexity is linear on. And now let's look at this loop here, two nested for loops. The first one runs from 0 to n times. And for each iteration of I, the second loop, the inner loop, runs n times. So we multiply these two since these are nested. And it would make it an n times n or n square overall complexity. In the second example, let's look at a constant time complexity. So if you have a loop that iterates a fixed number of times, regardless of the input size, the complexity is going to be O1, indicating that the execution time is going to remain constant. So here's an example. The I is initialized to be 10, and there's an input variable, but the operation doesn't depend on any of these. So it doesn't depend on the input size, it will be constant. And here's another one. The for loop does have the variable in it, and it does depend on the variable, but the input is given as constant, so the overall complexity of this loop is also constant, making it O1. Here's another example. At first look, this could look like an O log n because the variable I is multiplied by 2 each time, but n is constant, so this whole loop is constant time. Here's another one. We have the input size but that doesn't appear anywhere in the loop. So this will make it O1 because the operation doesn't depend on the input size. Another example here, we have what looks like a log n, but there is no variable here, so it's also considered O1. And for logarithmic growth, in a scenario where the algorithm is reduced, the reduces the problem size by half each time, like in binary search, we have a logarithmic growth rate, or O log n, and this is a highly efficient algorithm for large data sets. And here's an example of a log n. Runs this loop, iterates from 1 to n, but multiplying I by 2 each time, so it grows logarithmically because I doubles each time. Here's an example of an n log n complexity. The outer loop is O(n) because the I runs from 0 to n times, and then the inner loop for each iteration of this outer loop runs from 1 to n, but j is doubled by 2, doubled with each iteration. So when we combine these, it will be O n log n complexity because they're nested and they're independent. So here are some lecture examples. Again, this is a constant one. Doesn't really depend on the input size, the operation. And here is a linear growth rate because there's a loop, runs from 0 to n, so it grows. The processing time is going to increase as the input size n increases, so in proportion to the number of inputs n. This is a linear growth, and I would like to look at an example that a lot of people guess wrong during the problem solving lecture, since the time is running. Let's look at this one right here. A lot of people thought that this would be an n log n complexity, but there's no variable here, so everything is constant. I is initialized to be 100, and it's going to be decremented by 1, and is going to run till I reaches greater than -1. There's no equality sign here, so the inner loop's time complexity will be log I, but I is constant again, it's 100. So since there's no variable, it's O1, and the inner loop will run for each iteration of this I, and then every iteration j is going to be half by 2, so the inner loop is going to run log base 2 100 times and -1 because there's no equality sign here. So for the first iteration, this is going to run 6 times log 100, and this is going to run 100 times, and then the next time it's going to go back up. In the next iteration, I is going to be reduced to 99, and the inner loop is going to be log 99. So again, it's 6. So it's going to go on like this, and the outer, so this makes the outer loop's time complexity simplifies to O1, and also the inner loop also simplifies because they're both constant, so we are going to say this is constant, not n log n. So if that function was something like this here, if this was dependent on the I, then it would be O(n). But here, like, let's say we had an we had a variable n and an input size m, and the inner loop is dependent on m and the outer loop is dependent on n, then this would be an m log n. And we can't simplify these the complexity is m log n because they're not dependent, and they're nested loops. So if they weren't nested, then we could say m plus log n, but we still wouldn't be able to simplify this to om because we don't know the relationship between n and m. And if this was n in both loops, then the variable will be the same, so it will be n log n. And if they weren't nested, then we could say n plus log n, and it could simplify to O n. That's it. Thank you.